Hi, everyone. Thank you for joining us for today's webinar, Blind Spots of Low Voltage Testing with Drew Norman. I'm Meredith Kenton, MEGGER's Digital Marketing Specialist, and I will be moderating today's webinar and helping answer questions. If you have any questions about webinars in general or this webinar, feel free to email me. And if you have questions during today's presentation, I encourage you to submit them on the panel on the right side of your screen. It should look like this one. At the end of the presentation, I will ask Drew as many questions as we can get through in the time that we have. And if your question isn't answered, we'll make sure you get an answer via email after the presentation ends. And on that note, I'm going to hand it over to Drew Norman, our Senior Applications Engineer. It's all yours.
Thanks, Meredith. Hello, everyone. Good morning, good afternoon, good evening, wherever you are in the world. Welcome back, or welcome for the first time. For those, this is our fourth installment of our webinar series on motor testing. Again, as Meredith mentioned, we'll be covering the blind spots of low voltage testing. So today we're going to be covering, we're going to go over these big 5 critical motor tests, and they're listed here. Okay, so the low voltage testing, Kelvin resistance testing, nominal DC testing, often referred to as MEGGER testing, are pretty common. Like most of us use that in our motor testing programs. So we're going to talk about the benefits of those, of course, but then how these additional 3 tests, high voltage DC testing, surge testing, and dynamic testing, can enhance a program. What we're missing, what are the blind spots, again, of just doing the 1 and 2? How can we better equip ourselves to understand our motor condition and the environment that our motor has to live in by adding some additional testing? So that's the focus of this webinar. So let's start off talking about Kelvin resistance testing. So low voltage resistance testing, when performed specifically on motors, is looking directly for imbalance conditions. So oftentimes we don't know exactly what the resistance should be of a motor because it's not something that we find on the nameplate, but we know that for a 3-phase motor, for the most part, it should be balanced, especially for the larger the motor, the more balance that we should see. There's some inherent imbalance in lower horsepower motors that are randomly wound, for example, in some cases. So we do this precision balance measurement with the aid of what we call a 4-wire Kelvin bridge circuit. And I'm showing you the circuit here. Basically, we use a constant current source to pass current from the attached point in the motor circuit, typically at the terminals of the motor, or maybe even from the switchgear, and then measuring directly across 1 phase of that particular motor winding. And so we pass the current flow across that circuit and then measure the voltage drop across the circuit at the point of contact. And that eliminates any resistance of the lines that could contribute to that reading, and it makes it very accurate. And it's very important, of course, that we make good connection on either side of that clip to make sure we get a good reading. But if we do that, then we get a very precise measurement for each phase, and then we can do some evaluation of the balance of that circuit by one of these 2 calculation means, whether we take the full span, the max minus min, or a deviation from the average measurement of the 3 readings that we obtain, all over the average value, to determine the balance of the circuit. Now, unfortunately, there's no established standard for that balance, but we recommend, if you're testing directly at the motor terminals, that balance be less than 3%. In most cases, we expect on the order of 1% or less. But again, as I mentioned earlier, there are exceptions, such as concentrically wound random motors. Those types of windings have some inherent imbalance due to the nature of how the coils are laid into the slots. And of course, if we're comparing values to standards, so if we're an OEM, for example, if we're a manufacturer and we know exactly what the winding resistance should be, we could use that as a standard as well. But we have to remember that for that reading to be meaningful, we have to temperature correct that value. It's very common that those values are corrected to 25 degrees C, but there are, again, variations in that temperature correction standard as well. Some manufacturers might correct to say 20 degrees C. I've seen that one from a Japanese fork truck manufacturer before. So temperature correction is important because in a line-to-line resistance measurement, when we're measuring the resistance of a metallic circuit, like in this case, say copper or aluminum, those have they're directly related to the temperature, so that if temperature increases, that resistance will also increase and decrease as the temperature decreases. So it's important that we know exactly what it would be at a fixed temperature. Okay, so moving on from resistance, we'll go over some more details about each of these tests as we go through. This is more of an overview phase of this presentation. The DC tests, again, we're very familiar probably with MEGGER testing or insulation resistance testing at or around the nameplate of the motor. So if I have a 460 volt motor, for example, typically we measure that at 500 volts. Some folks measure that maybe 1,000 volts, but it's not intended to be a stressful test on the insulation. It's just an evaluation of the ground wall resistance value. That value can be measured and quantified so that we can compare it to standards, or we can compare it to past readings and see how that insulation resistance is varying over time. So it also, if we extend that, so a MEGGER test is typically 1 minute from the point of reaching test voltage. And we see here in the graph, what happens is we have this charging phase where we increase voltage to our test voltage, hold for, again, say a minute, and we allow the circuit to charge. Initially, we have this initial charging current, which is really defined by the circuit characteristics of capacitance, inductance, resistance, and the rate of change at which we get to test voltage. Once test voltage is achieved, we hold that value for 1 minute, and we allow that current to basically to decay asymptotically over time as the circuit charges, and then the insulation literally polarizes so that the molecules in the insulation are basically aligning with the electric field that we're applying during the test. And then at the end of 1 minute, we'll take that final leakage current and we'll take the voltage divided by that final leakage current, and that will give us the calculated resistance. So over time, if you're used to looking at a MEGGER meter and we see resistance increasing over time, that's this black line that we see here, increasing over time. But what's really happening is we're holding voltage constant and we're dividing that voltage value by this decaying current, which results in that calculated resistance. So it is important to keep in mind that resistance is a calculated value, not a measured value. So again, this isn't intended to be stressful. It's just, again, at the nominal voltage of the motor, we're trying to quantify that resistance for comparison purposes. Now, moving into high voltage testing, we're basically leveraging that same type of test that we did for the insulation resistance at nominal values and slowly increasing that voltage level to the stress level that it's going to have to endure during brief periods of time during its life. Namely, when we either start or stop the motor, anytime there's contact making and breaking, there's a potential for an inductive kick voltage or an operational stress that could be very high. And so we want to make sure that the insulation is capable of handling that stress. And one of the ways we do that is through this, well, of course, the conventional high pot, which is very similar to the test I just showed in the previous slide, except that the test voltage now is at least 2 times line voltage plus 1,000 volts. At a minimum, that would be, say, like a field testing requirement, maybe even higher for quality testing. But as far as the test is concerned, it's exactly the same test, just done at a higher voltage relative to the nominal nameplate value. So another more illuminating, if you will, test is the step voltage test, which basically is the same kind of test, except we do incremental steps to test voltage. So we walk it up slowly and evaluate the leakage current at each of these steps and see if it has a very linear response. And so that's what we're looking for there. The linearity of that response basically lets me know that the resistance, the insulation resistance, is staying at a constant value throughout the test as I increase the stress. And that's what we want to see. If we start to see a departure from linearity, isn't necessarily a test failure per se, in that it's not tripping on overcurrent or causing an arc, but we just start to see the nature of the resistance start to change its characteristic. And again, that departure from linearity is probably one of the most predictive indicators that our ground wall insulation resistance is, our ground wall insulation system is starting to degrade. Okay. Now, another high voltage test that we do is called the surge test, and the surge test is valuable in that it looks at the copper to copper insulation, which is a different barrier. So over here on this graphic, we see the ground wall insulation represented here in the slot between the conductor and the frame. The turn-to-turn or copper-to-copper insulation is between individual turns in the coil. It could possibly be between two adjacent coils, so copper-to-copper between coils. And if those coils happen to be in different phases, so if the top coil was, say, phase A, the bottom coil was phase B, that phase-to-phase barrier is also considered a copper-to-copper insulation barrier that we need to evaluate. And so when I do MEGGER testing, insulation resistance evaluation, whether it's low voltage or even high voltage with the step voltage test, I'm only evaluating this portion of the insulation, not the individual turns or the coil to coil or the phase to phase. So surge testing enables us to look at that insulation, which is also stressed again during those start and stop intervals, switching intervals. Okay, and of course the surge test, how it does that, right? So we charge a capacitor with a certain amount of energy, and we release that energy into the winding. And the winding here in this graphic is shown along the bottom, kind of isometric graph, if you will. And so like our T1 lead or our U1, if you will, would be the point of connection here. And as the surge voltage and the current flow that results from that release of the capacitor penetrates the winding, there's a non-linear voltage characteristic that's developed across that coil. And this establishes some voltage difference between adjacent turns within the first coils, so that we can evaluate that copper to copper or turn to turn insulation. And if there's any insulation weakness there, we'll look at that in the form of variation in the surge waveforms that result for each of these phases. So that's kind of what we're doing there with the surge test, again, to evaluate a different part of the insulation system that low voltage testing would just miss altogether. Okay, and then the fifth test and the critical five is dynamic testing. I had a webinar last week where we covered an introduction to what dynamic testing is about, what kind of parameters it's looking at, how can it help us. Here are some of the highlights. Dynamic testing is performed while the motor is in operation, which is good because hopefully our motors are running more than they're not running. So there's a lot of opportunity to evaluate the dynamic condition. It evaluates the power quality, the motor operation and its response to that power quality, and the motor operation in response to its load as well. And of course, the load is evaluated. And these are all potentially heat producing conditions, right? And we know that heat's the #1 attacker of our insulation system. In our introduction to static testing, we covered that quite thoroughly. If you've missed any of those past webinars, they are available on our website too. You can go back and watch those videos. But excessive heating effectively leads to insulation degradation. We said that for every 10 degrees C rise in the stator insulation temperature, we could potentially lose as much as half of that insulation life, or the rate of degradation doubles, if you want to think about it that way. Excessive loading can also accelerate mechanical failure. So in addition to heat, we also have mechanical stresses that are applied by increased load. So dynamic testing helps me, by looking at all these different parameters, by connecting the motor while it's running, I can evaluate the environment that's going to create heat or create additional mechanical stress, or even evaluate the actual condition of some of the mechanical components, which is it's a vital piece of understanding the system and what we can do to potentially improve the system and the environment that the motor has to live in. So in static testing, even in dynamic, we covered this curve. This is the installation life curve. If we care about when our motors are going to fail, when we consider that from an electrical standpoint, it's the breakdown voltage of the insulation that we have to consider. And we know that the breakdown voltage at the beginning of life starts at a very high value. We've mentioned that several times. I'll go into why that value is so high now. But then over time, as we put the motor into service, that breakdown voltage is going to degrade over time as the heat affects the insulation. Eventually, it's going to lead to motor failure once the insulation can no longer withstand the switching surges that I discussed earlier, or of course, once it drops below the bus voltage, then it's just going to fail either to ground or phase to phase or wherever that insulation is weakest. Now there might be another motor of the same design that fails in half the time, and the reason is probably because it has to endure a harsher environment. There's more heat present, or the stresses are different. Maybe the starting interval is more frequent. Lots of different factors there. And to help us understand the differences between the operational conditions of motor A and motor B, that's again where dynamic testing kind of comes in to reveal those factors that can push us towards a shorter life, a less reliable operating environment. So that's kind of how dynamic testing fits into the mix. So now we'll take some time to talk about high voltage testing and hopefully clear up some confusion. A lot of times when we bring up the word high pot, there's people cringe, or they have some past experience where they saw high pot potentially cause the motor later on, to experience a failure. At least that's the perception that was noted because a test was performed and then the motor failed. So let's talk directly to that. So a couple things that we have to keep in mind about motors and their design criteria is that there's a couple of different voltages that we're discussing here. It's not all just the same thing. And so oftentimes we're very familiar with a nameplate value. So this particular nameplate I have a picture of here, the nameplate voltage is 400 volts. And that voltage represents the operational voltage. So the voltage, of course, in this case, a three-phase AC motor that we would apply to make the motor run, right? To produce torque, to produce appropriate magnetic fields and have the right current draw so that it produces the correct amount of horsepower or kW at a specific speed to drive our load properly, right? That's what that voltage is about. And then we also have to consider there's the actual stress that the motor has to endure. So while we're applying 400 volts during these make and break of the contactor, we have voltage spikes or operational voltage stresses that far exceed that nameplate voltage. And there's documented evidence, empirical data that's been collected in the field by engineers that show that value can be as high as 4 times the nameplate voltage. So there's a significant potential stress there that goes well beyond that of the nameplate. And then of course we have the voltage that's associated with insulation design, and that was the graph I just showed you prior. That at the beginning of life we want a very high insulation integrity, breakdown voltage, if you will. And then as the motor lives out its life, that breakdown voltage will decrease over time, and that allows us a longer period of time. So again, operationally, we want to maintain the nameplate voltage during operations within a certain range, right? We don't want to get too high. High voltage can cause saturation of the iron, and that's going to heat the iron from the outside in. That's not good for the insulation. But it's not that we're worried about overstressing the voltage from a potential breakdown standpoint. It's the saturation of the iron that we're concerned about in that case. And then from a low voltage perspective, we don't want to be under voltage, because then operationally, for the same amount of delivered power, I'm going to have a higher current. And that higher current, of course, is going to produce heat in the form of I squared R losses. Okay. So as I mentioned before, operational voltage stresses, high breakdown rating is necessary to withstand the switching surges, which can be as high as 4 times the nameplate voltage. And as an example, a 460 volt motor at the beginning of its life has that breakdown voltage of 28,000 volts, and we saw that in the graph. And this is where we get that number. So if you looked at that individual slot, The enamel coated wire, this is a random wound motor, right? 460s are typically random wound or mush wound, sometimes they're called. And that randomness refers to the geometry. So that turn one isn't necessarily next to turn two. There's no fixed geometry. They're just kind of coiled up around a spooling fixture and then placed into the slot. But each of those turns has an enamel coating, and that enamel coating has a breakdown voltage rating, or is past a high pot at some point in its life, AC high pot of 8,400 volts. And then we have an additional insulation barrier that we place between the coils in that slot and ground. And this is typically some kind of Nomex or composite material that includes Nomex, which has a breakdown voltage of as high as 20,000 volts. And we've actually done these measurements in-house in our laboratories at Baker, and this is proven out. These insulation systems are really this strong. Cumulatively then, the insulation breakdown voltage of a 460 volt motor at the beginning of its life is approximately 28,400 volts. And now I wouldn't suggest we ever test a 460 volt motor to that, and we couldn't, because what would end up happening is we'd ionize the air around the outside of the coils, and we'd get partial discharge across that from that external uh, uh, ionization to ground, and that would cause our current to trip, but it wouldn't be breaking through any insulation barriers. It'd be externally to the portions of the coils that are outside of the slot where a lot of that discharge would occur. And again, it's not super valuable. We're not stressing that level, so there's no need to test to that high voltage level routinely. But what we want to do is test to the operational stress. Okay. And again, the reason they're designed this way, this highest voltage at the beginning of life, is so we have room to degrade over time. If I want a motor to last 10, 15, 20 years, I'm going to have this high insulation capability at the beginning of life so that it has room to degrade over time. Of course, we showed this graphic in the static testing where periodically testing to evaluate that we're in the good zone, we start to see some departure from linearity, or maybe even surge pulse to pulse EAR indications, and then that would give us some predictive indication that we're arriving at the motor failure zone soon, reaching the end of life, if you will, so that we can start to take proactive measures to plan a change out or clean and inspect or whatever is required to maybe move us back up into the green zone. Of course, once the tests start to fail, then we're near the end, and we just definitely have to plan on changing out the motor. But imagine if design engineers didn't start us off this higher value. What if it was just a 2,000 volt insulation to ground for our 460 volt motor? Well, the room to degrade is far less, and of course, once the switching surges, which are at test voltage, or in some cases are even above the test voltage, those are going to cause internal arcs, which are going to accelerate that insulation probably even faster. So it's more likely that our curves would be really small. These motors would last for very short intervals. And of course, you'd probably take that manufacturer and tell them you no longer want their products. So you can see why it's important that they design them this way. And all we're doing is leveraging that high voltage capability of the insulation system to evaluate its change, right? So as it begins to show a nonlinear characteristic, for example, then we get indications. If we just did low voltage testing, if I'm just doing MEGGER testing, I'm down here around the motor fail zone. By the time I have indications that the insulation is beginning to weaken, it's probably too late for us to even take action, if we even find it at all. So another concern, again, I mentioned earlier, I saw this motor get high potted, and then we went and did the test, and then we went to run the motor and it failed. Oftentimes, older test equipment's to blame for some of those stories, where vintage test equipment relied heavily upon the experience and technical ability of the testing technician or the engineer that was running it to be dutiful, to watch that current level, and if that current level started to take off, maybe we're looking at an analog meter, or maybe an analog, even some kind of analog digital indication where we see a bar increasing over time, to stop increasing voltage or stop the test, and not necessarily have any kind of active or automated tripping circuit, if you will, or some means of slowing down the test. So today modern test equipment like the MEGGER Baker AWA, DX, and our future products will take the guesswork out of any of that, so that it basically won't allow you to do more um, significant damage that could come from sustained levels of voltage where the current levels, leakage current levels are high. So that's another thing that you can have a little more confidence in modern test equipment. Again, we have arc detection circuits that look for instantaneous changes in voltage and immediately stop the test to limit the current. Of course, if the current changes um, a little more slowly, but the rate of change of current starts to increase, we can also stop the testing there. And of course, we have instantaneous overcurrent trips at several levels that can mitigate, again, the level of current that's going to cause carbonization, if you will, of the insulation. And of course, when we do surge testing, we have this threshold we call pulse-to-pulse EAR, which stands for error area ratio. Basically, what that's doing is looking at the stability of that waveform. If the waveform starts to shift around, that PPAR will basically quantify that shifting and stop the test, so that we don't, again, continue to surge while an indication of weakness has been detected. So here's some cases, and again, reiterating some of the value of each of these tests. So going back to low voltage, again, I mentioned earlier, we're typically looking for imbalance in the circuit, and those imbalances are caused by high resistance connections. Most often, probably the most often found problem with resistive imbalance and high resistance connections is that in the terminations of the motor in the junction box, termination crimps. But it could be contactor surfaces that have been pitted over time. They don't have good contact. If we're testing through those contactor surfaces, of course, maybe ferrules in the fuse. Fuse connectors can become loose over time, or maybe some flaws in design, who knows. Those things can lead to high resistance connections. Loose or over tightened connections can also lead to high resistance. So those are the typical things that you typically find in the field. Of course, it could also be caused by improper motor circuit connections. If you have a motor that came in from a manufacturer or a rewind facility that had been mislabeled or wasn't properly labeled or labeled at all, could potentially hook up the leads improperly and not get the Y connected properly, as an example, and that would lead to imbalances as well. So that kind of testing on the front end will definitely help us out. If we had turn-to-turn fusing in the motor winding, that could also be detected, but by the time that's occurred, it's more likely that the winding has burned itself up by the time, and so it's not stressing that insulation between turns. It would have to be a turn-to-turn fusing that has already occurred before the low voltage resistance test is going to be able to detect that type of failure mode internal to the winding. That's where surge test comes in, right? It looks at it proactively while the insulation is just beginning to weaken. So here's a case where we have a 4.7 resistive imbalance, and you can see the corrosion, probably an improper crimp here, a loose connection is causing high resistance to occur in those particular connectors. Low voltage resistance, the insulation, doing that MEGGER test again is great for evaluating low MEGGER readings, which are typically caused by intrusion and by contamination or moisture. They'll also play out in the form of low polarization index or dielectric absorption testing. Surface contamination build could have an effective increase in PI if it increases the capacitance. So it's a little, we have to evaluate it on its, there's a little more to the evaluation of how we determine, but depending on if that contamination creeps into the junction box, for example, that's effectively going to lower the PIs, lower the MEGGER readings, but there is a potential for, just on the winding external, not to the electrical connections, but external to the insulation, to effectively increase the conductive path of the coil and effectively the effective surface area of the coil, and the capacitance could increase, causing PIs to actually increase over time. So it's a little open for interpretation there, but again, primarily measuring MEGGER readings and installation resistance readings over time, and as they lower, give us a clear indication it's time to do some cleaning in specs or clean in place or pull the motor out for cleaning in a shop environment. Here's a couple of examples of kind of how the qualitative feedback we get from a PI or a DA. Here we see a couple of examples. Moisture, for one, has a telltale indication of oscillation. So the presence of moisture, because water is a dipole, right? The polar nature of the water molecule moving, flowing as it does in liquid form, that movement of charge causes it to oscillate. And so we see that up and down current. It's about, I mean, you could ferro a line through that and you can see that we have a good PI here, the change in current over time, but these values can swing erratically quite a bit sometimes and could alter our PI readings. Over here on the right, we see the effect of contamination, and specifically the type of contamination that's giving a surface leakage path around the insulation system, where it flattens out the curve in such a way as the insulation isn't really being measured anymore. We're just seeing the sustained level of current because of a parallel path caused by that contaminant from the conductors to ground. So again, a lot of value in this low voltage stuff, but again, this isn't stressing the insulation anyway. It's just of quantifying the resistance to ground. So PIs are also, and DAs are also valuable in evaluating age, but only when the winding's clean and dry. We have to get that contaminant out of the circuit so that we know that we're looking only at the insulation resistance effects on that current changing over time. And this graphic, kind of illustrates that nicely, that over the years, we see a slowly degrading change in current. Okay, a PI is evaluating an early reading at about 1 minute to the reading at 10 minutes. The DA does from 30 seconds to a minute or 30 seconds to 3 minutes, and we evaluate the change when it occurs earlier on in this, more quickly, if you will, for smaller motors typically. So again, by evaluating that change in insulation and the insulation's ability to polarize, we can kind of have an assessment of whether it has good mechanical integrity or not. But again, that requires a clean and dry environment. Unfortunately, we don't have that in the field, so this is a test that's primarily reserved for an age evaluation process in a shop. However, the PI and DA, as I showed you in the previous slide, are used as a qualitative assessment of the infiltration of contamination or moisture into our circuit response. So again, if I have low MEGGER readings and I have a flattened PI, then I right away know that I have some contamination path affecting that circuit. And depending on where I'm testing, I can begin troubleshooting, understanding where that contamination is present. Maybe it's just the nature of that environment. Maybe it's something new, right? We can use trending to kind of evaluate that as well. Now, as we move into high pot, and specifically we recommend the step voltage testing because there's just so much valuable information that comes out of step voltage testing in the form of this linear response curve. And here's a great example of two identical motors. These are 4,000 volt motors. We do this incremental stepping of the voltage. That's the cyan color there is the voltage level. And the red represents the charging current and then subsequent leakage current at each of these steps. And we see this asymptotic decay, which is normal. These little spikes represent scale changes, nothing to be concerned about there. But we evaluate this final leakage current values in such a way as that they basically line up in a linear way. And that green line that we can draw between those triangles represents the resistance of that circuit. And if the resistance is constant from the lower voltage testing here around 3,200 up to 9,200, this line will be straight. And if, as we see in this other curve on the right, if it starts out linear and then it begins to depart from that, that means that the resistance is starting to go down and that the insulation resistance is approaching its breakdown voltage. And the other interesting feature in this particular graph is the erratic current that occurs at the highest voltage level of around 9,200 volts there. And so I would bet that if I tried to go an additional 1,000 volts, that motor probably would fail on over current. And so I know exactly where I am on the breakdown curve, you know. Okay, so finally, surge testing. I've talked about that turn-to-turn, copper-to-copper, phase-to-phase relationship earlier, but that no other testing is going to evaluate. So it's super critical because according to some studies, 80% of winding failures begin first as a copper-to-copper insulation failure. Then once the copper-to-copper touches off and it fuses, that it's going to have an internal effect we call the autotransformer effect, which causes the motor to exhibit a lot of internal circulating currents, which go undetected by your protection circuit, that causes your winding to burn up. And I'll show you a picture of that here in a second. They're also surge testing is evaluating copper to ground to some extent. It's not the entire winding, but just that front end. But we use this pulse-to-pulse EAR graph as a tool for any spikes that we see in this graph would be indicative of insulation weakness in these particular locations. And here we see an example of the shifting waveform, which is caused by, as the insulation arcs over internally, that causes an inductive change. The small inductance change causes the resonant frequency of this ring pattern to shift to the left. And that is represented in the PPAR graph as spikes or increases in the PPAR graph. And this is what we use for our protection, if you will. So turn-to-turn faults that occur in the coil, eventually that turn-to-turn fault, if it, before it burns through the ground wall or before it burns face to phase, will have this high current flow internally, and you can see these localized heating that's occurred. And it started out in just 2 adjacent turns and then slowly burns up these 3 coils till eventually this motor fails to ground as it exits the slot on that first coil I'm pointing to there. So PPAR is our kind of a telltale indicator that's going to help us mitigate this type of failure mode from causing a motor failure, a premature motor failure in our plant situation. One other thing I'd like to point out about surge testing, and our DX is capable of this type of testing, is looking for partial discharges that occur within insulation. So surge testing can excite internal ionization if there are voids in the insulation internally that go unseen. And this is another failure mode that we need to be concerned about for high voltage motors, but also for low voltage motors that operate on variable frequency drives. Because of the rapid switching rate, ionization can occur internally, producing chemically active gases that attack the insulation internally and can also lead to turn-to-turn failure. So quantification of partial discharge is also potentially an important mechanism that we have to evaluate during the surge test. And I mentioned before, dynamic testing, again, is going to help us understand the environment. Here you see another motor that's been burned up. It has localized heating. This is a different pattern though, right? It's like a third, or actually in this case, 2/3 of the winding have been overheated. This is caused by a high voltage imbalance, probably caused by high resistance connection, or in this case, probably a single phasing event. So looking at power quality helps us identify voltage imbalance that can lead to this kind of uneven insulation degradation over time, probably to a lesser degree, but again, our winding is wearing out at different rates. Higher low voltage that I mentioned, saturation and higher current. And of course, distortion is an instantaneous voltage imbalance is the best way to describe distortion. And so again, identifying those conditions that maybe we can correct before it has the opportunity to really cause heating damage to our insulation system. Dynamic testing also gives us some clarity on rotor bar health, especially in our induction motors, how efficiently our motors are operating, and of course any other kind of mechanical defects like severe bearing faults. Okay, and we'd be remiss if we didn't talk about dynamic testing to point out that torque, right, is telling us directly what's going on with the load, process overloads, improper application, cavitation, which is what's shown here. We can just qualitatively see that that's a problem. gearbox related issues, belt related issues, and the list goes on and on. If you're interested in this torque stuff, come back in 2 weeks. Leslie Reed is going to be doing a webinar on how torque is being produced. It's called demystification of torque. She's going to help us understand how we take voltage and current and get to this mechanical readout of what's going on with the load. Very interesting stuff. Speaking of that, upcoming webinar schedule, again, May 28th. That's 2 weeks from today. Leslie will be giving that torque demystified. If you're interested in other topics, go to the MEGGER website there in the US, us.megger.com/webinars. And then you can see there's some really interesting stuff that's coming out on those. Highly recommended. Okay, with that, we've reached the end of the presentation. If there's any questions, I'd like to take those now. Got some time, looks like.
Yes. Okay. The first question is, which is more critical, high pot or surge?
High pot or surge? So they're different. A high pot is evaluating the ground wall insulation. Surge test is primarily looking at the turn-to-turn insulation. So I don't think that we can make one more important than the other. Although, again, I did mention that 80% of the insulation begins as turn-to-turn faults. So if I had to give a little more weight, I would put it in the surge category. But high pot testing evaluates the entire ground wall insulation. So again, it's one of these cases where neither one replaces the other. They each tell us a little bit of something different, but surge test is probably the primary driver towards most electrical insulation failure.
Okay. The next question is, does high voltage testing damage my winding?
So potentially, I guess, is the most honest answer, but here's the thing to keep in mind. So as I mentioned earlier in the presentation, the highest operational voltage stress to be upwards of 4 times nameplate. And that occurs anytime there's a breaking of the circuit. The making and breaking of the contactors produces inductive kick voltage, which is stressing your insulation system. When it does this, it could produce arcs, and if the insulation, and it definitely is causing insulation damage during those switching intervals. And if there is weakness found there, you have all the current of the distribution system that's going to flow through that weakness. When we do testing, either high pot or surge testing, we're doing it at the same, or potentially even a little bit lower than the operational voltage stress, but we're evaluating that current level that may exist or any instability that may exist so that we stop the testing as soon as that weakness is found. So high pot testing and surge testing could slightly degrade the insulation system, but it's miles away from the insulation degradation that occurs from the actual operational stress that the motor has to endure. So then it's designed to handle typically, right? So that when we do these tests that are higher voltage, it is going to allow us to see that weakness without causing any excessive damage that the system isn't going to induce on its own.
Okay, the next question is, what is the normal design life of a motor?
Okay, so it kind of depends on the motor manufacturer, right? They typically design motors to last anywhere from 10 maybe to 20 years. I think the more important question is how long should I expect my motor to last in the field? And regardless of whether it was designed to last 20 years or 10 years, if I put it in a condition where it's in a high moisture environment, I start and stop it 100 times a day. I put it on a transformer that has high voltage imbalance, on a bus full of VFDs that have high harmonic content. That motor's not going to last 6 months. So again, using dynamic testing to evaluate those operational conditions will get the most out of that design. And as far as the design's concerned, that's more of a question for the design manufacturers to answer. But as you understand the operational condition, that allows you to get the most out of that design, which I believe is a more important question.
Okay, the next question is, what is the accepted voltage for surge testing?
So surge testing is there's a couple of standards that we use for surge testing. The IEEE standard, which is IEEE 522, gives us a formula, which I don't have handy on the slide to show you, but basically it uses the per unit values. So per unit is this like way of getting the equivalent DC stress per phase. So for 460 volt motor, we divide that by the square root of 3, multiply by the square root of 2, and then that kind of gives us the 1 per unit, and then we multiply that by 3. It's actually like 3.1, something like that. They multiply that by, and that gives you your test voltage. What Baker recommends um, is a 2 times line voltage, so 2 times whatever the line voltage value for 40 volt or 460 volt motor, that would be 480 volts. 2 times that, which would be 960 volts plus 1,000 volts. So that's our formula. It's a little bit easier to remember than all that square root of stuff. IEC has a quality testing standard for high voltage motors, high horsepower motors typically, that's 4 times the nameplate, plus I believe 2,000 volts on top of that. So that's probably the highest quality testing standard. There's also ESA, the apparatus repair standard 100, which is more in line with the 2 times plus 1,000. And I believe from a reliability standpoint, the most common accepted test voltage for motors in the field is that 2 times line voltage plus 1,000 that I mentioned.
Okay, the next question, let's see. Is high voltage testing recommended for a low voltage motor during normal operation?
So again, I think the question is while the motor's installed. Of course, during operation, we don't do any static testing. We definitely static testing, surge testing specifically, is only performed on motors when they're off, locked out, tagged out, verified, de-energized. But the evaluation of the winding, I'd highly recommend that you evaluate that winding again because it's the leading cause of insulation failure. It's the root cause, which is going to maybe show up as a phase-to-phase or a phase-to-ground fault eventually, but that turn-to-turn insulation is the first weakness that's probably going to occur in the motor. And whether you're doing surge testing or not, you're doing the same stress to your turn-to-turn insulation. You know, every time you start and stop, in the case of VFDs, every time those IGBTs or SERs fire on and off, those inductive kick voltages are stressing your insulation. So you're doing surges to your motor, whether you're testing or not. Doing the testing is just doing it while you're controlling the energy and evaluating the results. So you have the information that you would otherwise go without. So that so I absolutely recommend surge testing for motors that are in place, operational, while they're de-energized and offline.
Okay. Do you want to keep going?
Yeah, we can at least do one more. I know we're
Okay.
over a little bit here, but yeah, no problem.
Let's see. It says, early in the presentation, you mentioned that you can take measurements at the motor terminals or in the switchgear at the source side of the cable. If this is the case, what are the risks of doing it at the cable end?
Cable end. All right, so we're basically talking about doing at the motor terminals or from the switchgear. And again, it would be the load side of the switchgear, so not the source side. But on the load end of the switchgear, that's basically including the cables in that circuit. Now we don't we want to be probably within 300 feet or so of the motor so that we don't get reflective and wave impedance from the surge. But as long as the motor is reasonably close to the switchgear, there's little harm that's going to come, if any, or any amplification voltage that's going to occur from testing from the switchgear. What's nice about testing from the switchgear is it's convenient, right? So I don't have to go to the motor terminal, open the box, disconnect those leads, disconnect all, remove all the insulation, all that logistics that has to occur to get to the circuit testing points. So that's a big up. Now, The downside, of course, is that the cables are involved. If the cables have low insulation resistance to ground, it's possible that all I'm really evaluating is the cables. Although when we do the surge test, we still develop the turn-to-turn insulation, so we can see that kind of weakness. It might, the cables might mask the ground wall insulation readings or artificially lower, artificially lower PIs, because of the presence of contamination or moisture. If I'm testing cables, for example, that run through an underground cableway that's half full of water, that's obviously going to skew my results towards the lower, and it may not be an accurate representation of the motor. So we have to be mindful of understanding our specific installations and those specific challenges. Another challenge of really long cables is during DC testing, the charging current, that current at the very beginning of the, let's see if I can slide back to it really quickly. At the beginning of the DC test here, this charging current is directly related to the capacitance in the circuit. So motors with really long cables might have really high charging currents, and we'd have to reduce our ramp rates to get to test voltage in some cases. And I've been in some situations where we just couldn't test through the cables. So again, there's probably cases where we don't want to test from the switchgear, but a majority of motors, especially low voltage motors, we can do from the switchgear and minimize the amount of disconnections and removal of insulation, which could also lead to problems, right? Because we're handling stuff more often. So yeah, I think that answers the question, hopefully.
Okay, perfect. I guess we can stop there.
Okay.
Uh,
All right.
Thank you, everyone.